I'm Jeff, and today I'm going to be talking to you about this work on untelegraphable encryption, which is done jointly with Fuyuki, Ryo, and Takashi. So our story begins with the no cloning theorem, a very well-known theorem in quantum information, and it just says that given an unknown quantum state, this task of duplicating this quantum state into two is going to be impossible. But maybe a lesser known theorem in quantum information is what I'll call the no telegraphing theorem for the purposes of this talk, but it is sometimes also referred to as the no teleportation theorem. And so this is a related theorem which says that to take an unknown quantum state and deconstruct it into a classical string and then reconstruct it back into the state is also going to be impossible. One way to see this is that given the classical string, um, one can just run the reconstruction algorithm multiple times to then violate the no cloning theorem. And so, okay, so this is a related theorem. And one reason you may not have heard of it is because actually the converse is also true. In particular, in the information theoretic setting, a set of quantum states is clonable if and only if it is telegraphable. Um, However, if we consider the regime of computational efficiency, Neharan and Zandri actually recently showed that there are sets of states which can be efficiently cloned, but are actually hard to telegraph. And so a natural question to ask is, can we further leverage the computational hardness of telegraphing compared to that of cloning? And a very natural place to do this is in the realm of unclonable cryptography, which is just cryptography inspired by the no cloning theorem, which includes things like quantum money, quantum copy protection, and unclonable encryption, along with many more. And one thing that many of these primitives share is that they are actually very difficult to construct from standard cryptographic assumptions. In particular, they tend to need things like obfuscation and oracles, along with like maybe new conjectures even. Um, okay, so these are very hard to construct. This seems like a great place to try and see if we can work on telegraphability. And in particular, we're going to be focusing on the setting of unclonable encryption, which in particular is useful for building these other primitives like quantum money and quantum copy protection in certain forms. And we'll call it UE for short. So what is the setting here? In this setting, you have Alice and Bob, and they each share a classical secret key. And Alice can send quantum ciphertext to Bob, encrypting a message, and then Bob can decrypt with this key. So it's basically just standard quantum secret key encryption. Um, but what's interesting is the security definition. So we'll start with this notion of one-way security. This is modeled by a game between an adversary and a challenger, where the challenger is going to sample the secret key for the UE scheme and is going to encrypt a random message M, give it to the adversary. And then this adversary is going to try and split this ciphertext into two to two second stage adversaries who may be entangled but are not allowed to communicate. After that, these adversaries will get the actual secret key and both try to produce the message M. And the adversaries win the game if they're able to both produce the message M with some noticeable probability. Um, and so for this notion, we actually can construct this from standard assumptions, in particular without any assumptions, which was shown by Broadbent and Lord. Um, but perhaps this definition is a little lacking in the sense that it's not the most natural definition to have the message always be random. And so what you might want is something like the standard notion of semantic security, where the adversary selects two messages of its choosing, and then the challenger encrypts a random message back. And then the goal is for these second stage adversaries to now guess which of the messages it was. And they win if they guess it with noticeable probability over one half. It turns out that this seemingly innocuous change to the definition is actually a gigantic one, since we have no constructions in the plane model from any sort of standard assumption uh, for this particular notion. And so you might ask, like, why is it so much harder to construct this semantic security notion? Well, there's sort of like two main reasons. The first is that entanglement between these second stage adversaries kind of makes it difficult to use these standard search to decision techniques like Goldreich-Levin, and stuff of this nature. And the second is that we're sort of limited in the type of cryptographic tools that we can use because the second stage adversaries are learning the key along with some function of the ciphertext. And this is not a setting that is typically considered. So our techniques are basically just very limited for this type of primitive. And so what we aim to show in this work is that relaxing this definition to untelegraphability is actually going to be something which is both feasible and meaningful. Okay, so what is the notion that we consider? We consider sort of the untelegraphable analog, where the adversary now, instead of trying to split the ciphertext, it is going to try and classicalize the ciphertext by outputting some classical state ST. And then there's only going to be a single second stage adversary, which is then given the key and has to guess the bit. So then the remaining question is, so we can define sort of like whatever we want, but the question is like, is this a meaningful definition? And well, I would argue that maybe this particular one-time scheme is not the most meaningful. A few simple extensions of this will actually lead to some very interesting applications. So what do we actually show? So first we show that indeed we can get unconditional semantic security in the plane model for this one-time scheme. And then we consider several extensions. The first of which is this notion of collusion resistance, which is essentially just many times security, which we show from one-way functions. And something interesting about this is that this actually already separates unclonable encryption from untelegraphable encryption, because essentially what one can do is have the encryption algorithm encrypt the message twice, and by collusion resistance, this will be untelegraphable, but it'll be trivially clonable. A further extension of this that we consider is this notion of everlasting security, which just says that the second stage adversary can be computationally unbounded. And this is actually a very challenging definition to get, so we actually need to use the quantum random oracle model in order to achieve it. And furthermore, in the paper, we give evidence as to why this might be a difficult problem to solve in the plane model. Furthermore, we extend the aforementioned separation by showing that there is a UTE scheme that satisfies the one-time security, but for UE security, there's actually an attack which can basically clone the message information to an unbounded polynomial number of decryptors. And then, sort of lastly, in our set of main results, we show that we show a feasibility result constructing untelegraphable functional encryption. Okay, so given these sort of baseline results, like what applications can we show? Well, the first and sort of primary application that we show in this work is a new shadow tomography lower bound, which basically rules out hyper-efficient shadow tomography from collusion-resistant UTE. And we can actually even relax this definition to get not only a separation from one-way functions, but we can get this lower bound from pseudorandom state generators, or PRSGs, which are believed to be potentially even weaker than one-way functions. And previously, this type of lower bound required either oracles or post-quantum indistinguishability obfuscation. Either way, very, very strong assumptions. And then we further extend this by showing that even an even stronger lower bound. We show basically that hyper-efficient shadow tomography with unbounded post-processing time cannot exist if everlasting secure collusion-resistant UTE exists. So in particular, we show this in the quantum random oracle model. And then as a final application, we show how to construct a secret sharing scheme, which is for all policies, that is resilient to joint and unbounded classical leakage, which improves upon prior work that showed this for local leakage. Okay, so there's a lot of results here, but we're only going to focus on a very small subset of them. In particular, we're just going to show how to actually get semantic security, how to lift this to collusion resistance, and then from that, how to show that hyper-efficient shadow tomography cannot exist if one-way functions exist. Okay, so let's get into that. And so we're only going to need like one piece of background here to get into these constructions, and that's going to be non-committing secret key encryption, or NCE for short. This is something which functions just like secret key encryption, except that the encryption and decryption keys are going to be distinct. But it has the sort of special property that we are able to fake ciphertext. Basically, you can encrypt without a message and output something which looks like a ciphertext, and then sort of reveal to some message at a later point by outputting a corresponding decryption key. Sort of more formally, security says that basically the adversary is allowed to make a bunch of encryption queries, and then later we'll make a message query, M star, and then it has to decide whether the ciphertext and decryption key are going to be real or fake. And this can actually be constructed from one-way functions. Okay, but this is also going to be useful in the information theoretic construction sort of conceptually. So that's why I put it here. So as a warm-up, let's construct the semantically secure UPE scheme. So the main ingredients we're going to need is just a one-way secure scheme, which we can get immediately from one-way secure unclonable encryption, and then just a universal hash family, which is compressing. So what is the construction? It's very simple. The secret key is just going to be a secret key for the one-way secure UTE scheme, along with a random hash function from the family and a random string that we'll call R. The encryption is going to be an encryption of the one-way scheme for a random message, and then the string R prime, which is equal to R XORed with H of X XORed with M. And so you can sort of think of this string R prime as like a one-time non-committing encryption of H of X XORed with M. Okay, so with that in mind, how do we show that this is secure? Well, so recall the security game, and now let's plug in the actual scheme that we use. So our first step is basically just going to be to appeal to this like non-committing like property that we have, and switch the string R prime to be a uniform random string, and then decide the value of R sort of in the second stage by setting it to R prime XORed with H of X XORed with M sub B. And once we do this, notice that the ciphertext that the challenger sends over is going to be independent of this random message X, and therefore we can sort of appeal to the one-way security to argue that, roughly speaking, X has high entropy in the view of the second stage adversary, even given the secret key and this classical state. And given this, all we need to do is appeal to the leftover hash lemma to say that this R component is uniform and independent of the message and of R prime. And so this is all we need to show the security here. Okay, so with that, let's move into how to construct this collusion-resistant notion. So given the scheme that we just constructed and a non-committing encryption scheme, what are we going to do? So our construction is going to have a separate encryption and decryption key, just like NCE does. And we're just going to set the keys to be the keys from the NCE scheme. And the encryption itself is just going to be a simple hybrid encryption where we sample a one-time secret key, and then encrypt the message with the one-time scheme, and then encrypt the secret key under the non-committing encryption scheme. Okay, so how do we show that this is secure? So the game only changes a little bit here. We just need to now repeat the process of message queries. And so when we plug our scheme in, we're going to model it so the second stage adversary only gets the decryption key. This will be sufficient for our applications. And the challenger is going to get both keys, or sample both keys. And so all we're going to do is basically first switch this non-committing component to be a fake ciphertext, which then the decryption key will reveal. And note that we can answer the rest of the queries by the non-committing notion that we consider. And once we do this, basically there's no dependence on the secret key in the first stage. anymore for this one-time scheme. And so we can just switch this ciphertext to an encryption of 0, namely it's independent of the challenge bit B. And all we need to do is sort of undo this faking step to then we've sort of like fully switched like say the first query um, of this of this game, and then we can just go query by query to show that basically what the adversary sees is like independent of the challenge bit and argue security. And that's actually all there is to it. So all that remains to show is like why is this enough to rule out efficient shadow tomography? So to do that, let's go over like what actually is shadow tomography. So this is going to be a protocol where the procedure is given k copies of an unknown quantum state along with a set of m binary outcome measurements, sort of like whichever ones are your favorite, that act on n qubit states. And we're going to represent this by some circuit E, which basically takes in an index along with a state and outputs either 0 or 1. And the output is going to be a classical description of a quantum circuit C, which estimates the probability that the circuit E on I, phi is equal to 1, up to some error epsilon. And remarkably, this can be shown. It can be shown that this can be done with only a polynomial number of copies of the state. But one kind of issue here is that this capital M could be exponentially large, and so the actual procedure here could be something which takes exponential time. And so if we want something that's truly computationally efficient, this is the notion of hyper-efficient shadow tomography, which enforces that the runtime of the tomographer itself is efficient, along with the number of copies also being polynomial. And so for this, we need sort of an implicit description of the circuit E. Okay, so how is this related to untelegraphable encryption? Well, I think there's sort of like a very nice mapping that illustrates this. So the mapping is as follows. So we're going to associate the k copies of the unknown state with essentially k encryptions of the same bit B in the untelegraphable encryption scheme. We're going to associate the indices for this set of measurements with the decryption keys. So like each index will sort of act as a decryption key for the untelegraphable scheme. And then lastly, our circuit of interest is just going to be the decryption circuit of the untelegraphable encryption scheme. And with all this in mind, I think the attack should be pretty straightforward. Basically, all you need to do is query the message pair 0, 1 k times to get k encryptions of either 0, 0, 0 or 1, 1, 1, 1. And then just run the shadow tomography procedure to get some circuit C, which will allow the second stage adversary to just estimate what the decryption will output, and basically say if its estimation is less than 1/2, it's going to output 0. If it's more than 1/2, it's going to output 1. And as long as the error epsilon is less than 1/2, then actually this is going to win the game with optimal advantage. And so sort of one thing of note here is that it's actually sufficient to construct a UTE scheme which just has non-trivial security. So there's a bit of slack here, and that's really all there is to it to show that to show this result. So I'll conclude with some open problems. The first is to rule out hyper-efficient shadow tomography for pure states by showing a collusion-resistant UTE scheme with pure ciphertext. Notice that our construction is going to have mixed ciphertexts. And as I said before, non-trivial security is efficient for this. Another interesting question is to get everlasting security in the plane model, since this would give a very strong separation for this weakly efficient shadow tomography, where the post-processing is allowed to be unbounded time. And then lastly, more applications of UTE and untelegraphability, since I think this is a much more feasible area, which hasn't really been studied as much, but still seems to have some meaningful applications. All right, that's it.